All right, guys. I know this one is a long one, but we'll be able to borrow for 2 chapters, which is kind of exciting. And Gavin is coming back, which is really cool. And this is his area of expertise, this chapter, especially 18.6.
Something like that. Yeah. We'll get there. Yeah. Okay, so I'll do the standard advertising clause. So I'm recently started working at Rigetti Computing. We are going to build the world's most powerful computer using the power of quantum mechanics. So I'm senior scientist at Rigetti, and part of that is trying to figure out how to do quantum machine learning on this quantum machine, which we don't know how to do yet. Excellent. The partition function. So let's first talk about what partition function is and why we care. It's a little awkward because we skipped over the chapter on graphical models, but we alluded to in the previous talk. So the idea is that we get these graphical models, and sometimes we just draw them as a bunch of nodes. These represent my variables. This is my model of some probability distribution over these set of things. And then we'll draw little connections between them, describing how these interact. And this is called a factor graph, and it's sort of a convenient way of thinking about these things. So we're saying something like the probability of these things is equal to some set of stuff, which is determined by an energy. In the physics world, we tend to think about it as an energy. In the book, we just write this as some probability of these things, whatever the x's are, given some set of parameters. The idea is this p twiddle is an unnormalized probability distribution. It just tells you the probability of these things. It's some function that tells you the probability of this set of stuff up to some normalization constant. So we write underneath, make sure our probabilities add up to 1. We write the sum over the total set of things that could happen. And this thing is what we call the partition function. And often we use the symbol Z. Sometimes you see Q. And this was originally came from physics. So the term partition function originally referred to the partition of energy. So these kind of models are sort of bread and butter in statistical physics. When I'm thinking about the properties of something at thermodynamic equilibrium, something like the molecules of water in this container, we have some idea of how all those molecules interact. That's our model. That model tells us the energy way all those little molecules interact. And then what we actually care about all the time is this partition function, because that actually tells us a lot of the physics of the situation. So again, in some machine learning world, often they just write it as some function. In the physics world, we often write that this is some temperature and an energy, which is a function of coordinates and whatever our parameters of the model are. So this is our probability of x given our parameters. And again, this whole thing gets normalized by this partition function. And so what happens is, if I have some model like this, how do I evaluate it? Well, if I knew the set of the parameters already, I can evaluate this model using Monte Carlo, where Monte Carlo comes in most handy. But the partition function is a problem. If I don't know the partition function, what do I do? So there's 2 aspects to this. A lot of what people try to do in machine learning world is try to avoid ever calculating this number. Calculating the partition function is hard. In the physics world, we often have to calculate the partition function. So we'll talk about ways that you get that as well. So, yeah, definitions. There's some probability is equal to this partition function times some normalized probability, the p twiddle, And again, we often think of this p twiddle as being composed of an energy and a temperature. And again, often in the machine learning world, you set that temperature just to unity and forget about it. Although often it's useful to think about that temperature as itself a controller parameter. So what do we care about then? We're trying to find, we have some set of models parameterized by this fader. And what I would like to do is, given a bunch of data, and based on some models, I'd like to find the model that best fits the data. And well, I'm going to try and do this in the same kind of way as I did for a neural network, doing something that looks like stochastic gradient descent. I'm going to try to figure out what the gradient is with respect to the parameters over my data. So the important thing is the top line, well, one of the important things. So the gradient with respect to the parameters decomposes into two parts. Because this total probability, which I just put here, has these two parts. One is the partition function, and one is these unnormalized probabilities. So the first part is the change due to the unnormalized probabilities, and the second part is the change in the partition function. So what's happening here is when I'm looking for a good model, I'm looking for a model where that energy function is low. I'm looking for the low energy states. So I assign low energies to all the actual realizations I see from the data, that's good. But if you just did that alone, you would just settle onto a bunch of delta functions on the data states. What the partition function does is actually also encodes the entropy. It's trying to find, it doesn't like it when you try to get a little narrow distribution. It wants distributions that are wide and high entropy. And it becomes this balance between between high entropy and low energy. And these two terms are sort of balance between those two things. So just remind ourselves of a couple of useful facts. Again, what the partition function is, and then you also have to keep in mind this the logarithmic derivative. If you take the derivative of a log, that becomes 1 over the function times the derivative of the function. Yes. I'm going to go through them now. So this is the part. This is the part. These are the bits and pieces we need. Thing at the top is the thing we're interested in, and then I'm just going to go through what the significance of this long bit of math is. So the trick is, it's that second term on the right. That's what we're interested in. How do we evaluate this? And that's this long bit of math says, hey, actually, it's not as hard as it looks. So instead of writing it as the gradient, I've just written it as the partial derivative. And again, we're going to use this trick a couple of times. So the first line just says, I'm taking this partial derivative of the logarithm of the partition function. And then I've just written that out explicitly. Second line, I use this formula for the log derivative, pull out the partition function. The derivative now hits this unnormalized probability. Now comes the really clever, tricky bit. I now do this trick in reverse, and I put the logarithm back. So this part is becoming this part, and then I have the log over there. Great. The trick is that this part, hey, that's now the probability again of the just of the data. So now I have the sum over the probability of the data times this derivative. Well, that's just an average. So the net upshot is that this derivative of the log of the partition function actually becomes an average of the way that this unnormalized probability changes. So that's something you can calculate. And because it's an average, something you can calculate using Monte Carlo. You Monte Carlo across the data, and you evaluate this average. So it's become something you can actually calculate. This trick, this result, is actually most of what's in thermodynamics and statistical physics. It's sort of the central trick that we use all the time. without necessarily saying so. Yes?
And the thing that makes that trick is we know, random samples of X follow some distribution which we can sample in physics, right?
Well, okay, so in physics, the model in principle is given us by the physics. But that's not actually true. We actually make the models up as we go along and try to fit them to the physics. Yeah, so the idea is that because we have this form, that actually makes Monte Carlo kind of easy. Because I can always do this Markov chain kind of situation where I'm continuously trying to update and sample across this distribution. The trick is that, yeah, this quantity I actually want to try to minimize on the right-hand side, or find its gradient, actually becomes this stochastic average, which I can then evaluate using a Monte Carlo method. Any other questions on that part? So the take-home message, though, is that, yes?
Yeah. So is your intuition that if Z is some function of E squiggly, basically, you never actually have to evaluate Z?
No, that's exactly right. We're trying to avoid evaluating Z if we can possibly help it.
So long as it's a function of...
In fact, we basically, in almost any reasonable situation, evaluating C directly is computationally practical. So the trick here, as you said, is trying to minimize, trying to find these models without actually trying to have to calculate Z. So the basic idea of an algorithm, and the book talks about several, but they all really have much the same flavor to them, is that we're trying to find the first term, when we're trying to find this gradient, is trying to push us towards low energy states. And people call this the positive phase sometimes. And the other term is really trying to push us out and spread us out and increase the entropy. So the gradient, if we're going to do this a stochastic way, we're going to sample a mini batch of M samples from our data distribution. In principle, this first part is easy to evaluate. But then we have to sample, the second part, I'm actually sampling from the model distribution. So whatever my current fixed parameters are, I really want to sample from this model distribution, so I'm going to do that with a Monte Carlo method. And the different algorithms are really different in the way that we're going to pick out these model distributions. So the most naive way would just be to run a Monte Carlo algorithm and try to sample from that. The problem is you have this burn-in problem, that you just try to start from some random position. You got to run it for a long time to burn it in, to actually let it relax to the distribution you actually care about. And so that becomes very computationally expensive. Contrastive divergence, which is one of the examples they've given in the book, the trick is you actually start from your data distribution. So you're hoping your data distribution and your model distribution are actually not too far apart. So you start from your data that you actually sampled, and then you run a Markov chain Monte Carlo starting from those initial points for some length of time, and then let it relax closer to the model distribution. And then the other one, SML, stochastic maximum likelihood, there it does another trick. Instead of starting each time afresh from your data distribution, you just keep those samples you got from the previous model and keep going. The trick there is that each round of this, as you change the gradients, as you change the parameters, your model doesn't change very, very much. So your things you sample for the model distribution of the last step are actually pretty close to the model distribution of the next step. So you can use those and continue your Markov chain and get closer to your distribution. Any questions? So, yeah.
The second expression, you have. I just don't understand why this is gradient is exactly zero. What makes it? Oh, you have X tilde on the right, which.
Right. So those are meant to be sampled from the model distribution, right? So that's this expression from the previous page. It's saying that this gradient of the logarithm of the partition function actually can be rewritten as expectation over the model distribution. So those are situations, and there's a few other examples in the book. Those are situations where we're trying to fit the model to the data. But at some point, we often actually want to draw samples from the model. And that often means we actually need to know the partition function, because that's the normalization. The trick is that most of the time, we don't need to know the absolute value of the partition function. Typically, we need to know ratios of partition functions. And the idea is typically we have two models close by, hopefully. And the ratio of those partition functions tells us the relative validity of those models, for example. If we were, again, talking about a physical model, say this was the energy function of a small molecule binding to a protein. It's the same basic setup. I would use Monte Carlo to evaluate that. My partition functions could be two different drug molecules. And I would like to know which one binds better to the protein. This ratio of partition functions tells me that. So the trick is, how do I evaluate these ratios? Assuming your two models are not too far apart, which basically means their probability distributions have good overlap, then we play the following trick. We write down the ratio. We take Z1, and we're going to just write that out explicitly as our sum. And then we're going to multiply by 1. I'm just going to insert unity right in here. This is such a common trick in all of physics that sometimes we dress it up. Resolution of the identity is a phrase you see sometimes. But it's the standard trick. We just stick 1 in. OK. Doesn't look like you did anything. Well, OK. Trick is I then take this bottom P0 and combine it with this Z0. It's going to cancel out the Z0 that's in that P0. So now I get the ratio of the unnormalized probabilities averaged over one of the distributions. So again, I can calculate all the things in here using Monte Carlo. I can sample from one of these distributions, and in principle, I can calculate this ratio of these unnormalized probabilities. And that tells me this ratio. Again, the trick is, as long as things are pretty close together. So I wanted to just touch on this subject, although, yeah, because this was originally, this method is for what happens if my partition functions are far apart. What if, you know, I'm trying to look at the difference between this thing over here and this thing over here, but they're too far apart, there's very little overlap. What am I going to do? And in Neal's importance sampling, Radford Neal invented this, but it was previously invented in the physics world as what we now call the Jasinski identity. And as a physics, it actually ties into the second law of thermodynamics, how molecular scales machines actually work, the nature of time. There's a lot of physics. A lot of my academic research has been based around understanding the implications of that one relation. So Chris Jasinski invented that in the late 90s. Radford Neal basically independently invented it a couple of years later. And if you read his paper, you can sort of see the point where he realized that. It's like, oh, this is a good idea, this is a good idea. Oh, and basically the same idea has been discovered in physics. So the central idea is, I've got these two partition functions that are a long way apart. Okay, so I'll write this as a whole bunch of ratio partition functions. Each one is close to the previous one. So I have 0, 0 to Z1, Z1 to Z2, all these partition functions. That's going to be my total ratio. And if each one of those pairs is close together, then in principle, I could calculate the full partition function. Now, that would require doing simulations, Monte Carlo simulations, at each of these individual little steps. I'd have to burn in at Z0, at 0, at 1, at 2, at 3, at 4, all the way up to n equal to -1, and do a whole bunch of separate little simulations. Now, sometimes actually that's the right thing to do. If I actually cared about the partition function for the whole range between 0 and n, that might be the right thing to do. The trick is you don't have to. So the trick is to write again, this is an average over some probability distribution, again, of these ratios of all these unnormalized probabilities. If I did each one of these simulations independently, this big P here would just split up into a bunch of independent parts. P of x0, P of x1. The trick is you don't have to do independent simulations. The idea is that I start at 0, so I'll burn in a Monte Carlo simulation at 0, and I'll evaluate that first step. Now I'll do a single Monte Carlo update, relaxing with that new parameter. So that's not long enough for the thing to actually fully burn in and relax, but it moves it a little bit towards where it was going. And now I do another step. So I make an evaluation of this part that would actually become the ratio partition functions, but and then I do a single Monte Carlo step at that next parameter. So you never let it burn in completely, so you don't have to wait as long, but you still get the right answer. So the idea, I've got to sample somehow from all these different distributions. 0, 1, 2, 3, 4, 5.
And you don't want to do them all.
I don't want to do them all independently. I could do them all independently. I could just do x0, let that burn in, then do a separate Monte Carlo simulation at x1, and a separate one at x2. But that means I have to do all these simulations at all these different points. So the trick is that I don't have to do all of those. The trick is that I can actually do the whole thing in one go by only letting it relax a little bit between each step. So instead of doing x0 and making my evaluation, and then change the parameter at x1, and then doing a long burn-in simulation until I've relaxed to that model distribution at x1, and then evaluating the next step. Instead, I evaluate at x0, then change the parameter and only let it burn in a little bit. So it hasn't moved all the way across, but it's moved over enough that we still get good sampling. So then I do the next one, x2, x3, x4, x5.
I don't know what relax and burn in.
Okay, this goes back to the Monte Carlo idea. So that when we start a Monte Carlo simulation, a Markov chain Monte Carlo simulation, we have to pick some initial point. And that initial point won't be drawn with the right probability yet. And so conceptually, there's some probability distribution of my initial points. If I do many Monte Carlo steps, these Markov chain steps, eventually my distribution will be the correct model distribution. And that's what we call the burn-in time, and that's what I'm saying, it relaxes to the other distribution. So the trick here is that we don't have to let it relax. It's sort of, this distribution is moving towards the correct distribution, but it's never quite the correct distribution. It's kind of lagging behind, but it always has enough of an overlap that we still get good statistics if we have enough Monte Carlo steps. Yes?
Can you go back one step? Why is it important to find the ratio of partition functions? I think what you're interested in likelihood, in general likelihood of like what you're reading on the whiteboard, P1 versus some other model P2. Is that their idea? Why ratio of partition functions is important?
Okay, I'm going to give you the physics answer again, but that's fine.
I guess, I mean, partition function actually tells you everything about distribution, about all the moments you can do, if I remember correctly, it will be.
Yes, the derivative of the logarithm of the partition function gives you the moments.
Would you repeat your question, please?
I'm trying to, yeah, he wants to know a good intuition of why we care about the partition function, and I'm trying to think of a way of expressing that that's different from just going back to the physical intuition. So, I mean, okay, I'll just break down and do the physics. What happens with physics is that when we take the logarithm of this partition function, we get the free energy up to some temperature. And the free energy actually has two components. One is the average energy of the system, and the other is the entropy. So it becomes, it tells you about this balance between low energy and high entropy. So, yes.
What's the relationship between entropy, temperature, and energy? Is energy over temperature entropy?
Okay, now we're getting too far ahead. So temperature is the how fast energy and entropy change for a particular system. It's that derivative. In these situations, what it tells you is the trade-off between energy and entropy. How much energy am I willing to give up in order to get a more wider distribution? Tell me about that trade-off. So as you make the if you kept the energy function the same and turned your temperature down, you would relax down into sort of the lowest possible energy state. So one of the tricks that people play with the Monte Carlo is to actually keep the temperature in there as a parameter, and basically crank the temperature up high. So then you're sampling over a huge range of things, and then slowly crank the temperature down, and then that lets you relax down into the low energy states. And that's very useful when there's big barriers in your, we often talk about the landscape. When you're doing these Monte Carlo simulations, conceptually there's sort of this energy landscape you're trying to sample over. And if this landscape has big barriers in it like that, that can be very hard for the Monte Carlo algorithm to get over. So one way of getting over those things is to crank the temperature up. Now it doesn't see the energy barriers anymore, and then let it relax back down, and then it will drop back down onto the other side.
But is entropy times temperature equal to energy? No. Okay.
The derivative of entropy by the temperature. No, the derivative of energy by the entropy is the one over temperature.
Yes, but we're going to go too far afield into the physics, but yes, sort of. So actually, all I wanted to say, because I didn't want to get too sort of deep into all the details, calculating partition functions and ratio of partition functions is this is a huge subject. This is just poking at a few methods that people use, and finding these model optima is a huge subject. And a lot of the hugeness, the difficulty, comes actually from the Monte Carlo sampling. And Monte Carlo, like you said, what library to use? Markov chain Monte Carlo is very so a lot of the trick to Monte Carlo is picking those moves. If you pick a good move set, you will move across your landscape and you'll get good sampling. But what is a good move very much depends on the particular problem you're looking at. So yeah, you can get libraries for the easy bits, but the hard part is actually picking that move set. And then there's a huge range, and this is, at least in the physics world, we don't actually use this particular method really much. We use things that are related to it, but a little bit more sophisticated, involve basically doing samples in both directions, which actually gets you slightly better, somewhat better averaging. So there's a big, big subject, which is continuing to develop. Yeah.
Any question?
Sure. Questions?
Or is there more slide time?
No, slides. That's it for slides.
So I'm kind of still grasping at this, but I've heard this technique used with kind of placing GANs or measuring points.
Yes, but I don't know enough about GANs to understand how it's been used there. My understanding is, yeah, some of these methods get used in GANs in evaluating those probabilities. Yeah.
Can you show the slide with one before?
This one or the one before?
Basically, this function is one of the GANs. If you look at this log of p tilde, you can think of it as discriminating. There are variations which do that.
Okay.
Well, it's positive examples, negative examples.
So you're using the partition function instead of discriminator? Is that what happens?
Well, you try to
Oh,
avoid it, but basically you have to sample x tilde, right? And x tilde has to be sampled from distribution of p tilde. And then you try to learn a generator which matches the p tilde. And your biggest problem is estimating the entropy. Or gradient, actually.
So I think, a way to think about that is like you want like to positively reinforce a good example of something from your data, and then negatively reinforce something that's either like randomly selected or trying to proxy your data. So whereas, frankly, I can't remember, like in adjusted divergence, you'll take a, good data coming in, and then if it's Boltzmann machine, which I think is generally what the structure is referring to, you'll run it for a couple times, and then you'll get something that's no longer like a good input data, and you'll negatively update your model parameters data. So it kind of avoids those bad examples.
Okay, so like I link that back to Dean's thing, like, if you pick the daring sample, then it calculates, you're way off according to the partition function formula, and then like, that's too far off, let's go back. And you get another good sample soul or picture.
I think so, but like maybe in Don's example, it was like accepted or rejected, and this is like, reinforce good examples and then negatively reinforce bad examples always.
Do you have any experience with these automatic Hamiltonian samples?
Are these what?
Automatic Hamiltonian Monte Carlo samples.
Automatic Hamiltonian Monte Carlo samples. I'm not sure what you're referring to.
So Hamiltonian Monte Carlo is the one which is the derivative.
Yeah, so sure, Hamiltonian Monte Carlo, yeah, it's using, it's a mixture of molecular dynamics and Monte Carlo, yes. So it basically uses molecular dynamics, and basically uses the actual Hamiltonian of the system to figure out the gradients and move yourself along those gradients as if it was a classical mechanical system, and use those as the proposal distributions for your Monte Carlo steps. Yeah, they're pretty. It's again, it sort of comes back to this issue of finding a good move set that will move you through your parameter space. So those have this weird problem that basically what you're doing is you pick a bunch of velocities. You don't just have your x's, you have some velocities. And those move you through your parameter space and your forces, which are these gradients, which are changing those velocities. And then you have a Monte Carlo accept reject step. But you run into issues that you have to flip the velocities at times. And so the net upshot is you can still get this random walk. So the idea is to try to, one of the problems with Monte Carlo is this random walk aspect to it, which means that you sometimes, if your steps are too small, you just diffuse out very slowly, and you never get to where you go. So there's a way of trying to make these steps bigger in a way that is, yeah, it works. But it's, what do I say? It's yet another trick in the Monte Carlo toolkit. Put it that way. Monte Carlo is just one big toolkit of different ways of trying to come up with clever ways of moving through the configuration space.
Any more questions for Gavin?
So, sorry. So getting the partition function, basically this is a method of like how to get close enough rather than how to calculate that thing that's too computationally expensive.
Yeah, we're always trying to get close enough. I mean, that's anytime we're doing Monte Carlo, we're trying to get close enough. And Monte Carlo is a way of trading off close enough versus computation time. Yeah.
Can you talk about how you evaluate close enough? I know it's not so easy. That's the reason why I asked.
You're thinking of the burn-in time again. So there are some special cases where you can actually prove, you can actually demonstrate perfect sampling. But those cases are kind of not generally very practical. So the issue here again is, right, I have to start from somewhere. Then that distribution is not the proper distribution, and I have to run for some time. And after some time, I will be closer to the true distribution. I will never get exactly to the true distribution, because that takes, in general, an infinite amount of time. Except, again, there are certain very special cases where you can actually demonstrate you get to the right distribution after a finite length of time. But in general, we don't know we've got to the right distribution. And so it becomes a trade-off. If I go for very long and let myself relax, I'll get good answers, but it'll take me a lot of time. If I don't wait long enough, I get a biased answers because I won't have relaxed to my correct distribution. And yeah, people are really still struggling with the right way to really think about that trade-off. And I think you're right. Sometimes it's just people just eyeball it. But I've seen some recent work. John Jajera had some stuff about this trade-off between how long we should go versus samples versus bias, basically. It's trying to get the right trade-off between those two. So there is definite, people are still thinking about that, I think, trying to come up with better ways of doing that.
So I guess a little bit autocorrelation of sample change.
Yeah, looking at the autocorrelation is one way of doing it. Part of the problem with Monte Carlo is it will never tell you that you're wrong. So that, yeah, you look at the autocorrelation and whatever. One of the problems is, suppose your landscape looks something like that, right? And I start over here, and I sample over here really well. And you do autocorrelations or whatever, and you get, yeah, it looks really good. But the reality is you've never seen this side. And that's kind of one of the, that becomes very domain specific about understanding a problem and being able to find these problems and finding ways around them. But yeah, something like autocorrelation time will tell you when you relax locally into a good well, but it won't tell you about this more global problem.
It will tell you when you're doing really bad.
Yes, right. Oh, yes, question. Is there a question? Oh, yeah.
Could you discuss the difference between contrastive divergence and SML?
Yeah, it really just comes down to the way that you're picking out these samples, right? So I've got a sample from the model distribution. I'm going to Monte Carlo that somehow. How am I going to pick out that Monte Carlo? And contrastive divergence is just, my mini batch, I'm just picking out a bunch of data samples. And I'll use those as my initial points for my Monte Carlo. And then again, I'm going to pick some burn-in time. So the idea there again, though, is that hopefully your data distribution and your model distribution are not so far apart, so your burn-in time is not so long. And again, the idea with these things is we're trying to get closer and closer and closer. So we're kind of wrong when we're far away, maybe that's not a big deal. As long as we get the right answer, as we get, as long as we generally head in the right direction, and as we get closer and closer to the right model, these errors go away. Then SML is actually, does it more of a chain. It takes the previous distribution. So I've done some burn-in to the previous model. Now I've changed the model, but now I'm going to burn in starting from that distribution. So again, there, instead of hoping that the data distribution and the model distribution are close, you're hoping that the two model distributions one step to another and not too far apart, and therefore we give ourselves enough time to relax into the new model. Either way, there's going to be some built-in bias because you're never going to relax long enough. Okay.
All right. Thank you so much. As per usual, we'll be going to